This week on the Lectures in History podcast, Princeton University history professor Matthew Jones teaches a class on the history of artificial intelligence. He also discusses the debates over its development. Hang tight, class starts right after this.
This is Rachel from C-SPAN's podcast team, and before we get to this week's episode, I'd like to introduce you to my colleague Jen.
Thanks, Rachel. Hi, I'm Jen, one of the producers here at C-SPAN. And if you enjoy Lectures in History, we think you'll also like reading our weekly American History TV newsletter.
If you're into history, you'll appreciate being an American History TV insider. Every week, we deliver advanced program highlights so you never miss out on learning more about the people and events that document the American story.
It's the place to find out which Lectures in History, Civil War battle talks, features on the presidency, and interviews with historians are coming up. Plus, you'll get highlights of featured C-SPAN podcasts.
Subscribe today at c-span.org/connect for your weekly dose of history every Friday.
Thanks for being part of our community. Don't forget to visit c-span.org/connect to sign up.
This episode is brought to you by Shopify. Forget the frustration of picking commerce platforms when you switch your business to Shopify, the global commerce platform that supercharges your selling wherever you sell. With Shopify, you'll harness the same intuitive features, trusted apps, and powerful analytics used by the world's leading brands. Sign up today for your $1 per month trial period at shopify.com/tech, all lowercase. That's shopify.com/tech.
Today we are going to do our second lecture on the history of artificial intelligence. We talked about it way back in September. And today we're going to be talking about how it is that data came to overtake rules-based in artificial intelligence. So in 2009, a trio of Google researchers published a paper called The Unreasonable Effectiveness of Data. And what they said is that scientists and humanists alike had been looking for simple theories about language and other facets of human experience, things that would look like physics or mathematics. But it turned out embracing complexity, they said, was the way to go. Taking data at enormously scale and analyzing is what allowed you to translate language, to reproduce language, to understand pictures and whatnot. Data won out, rather surprisingly, to people of a mathematical mindset over rules. Not that long before, as we talked about some weeks ago, the progenitor of the term artificial intelligence, John McCarthy, had denounced the idea that learning from sensory experience from data would ever produce complex behavior. But in 2009, the opposite seemed to be true. And today, that's what we're talking about. How is it that we came to be in this situation? Now, in the last, say, 7 to 8 years, the term artificial intelligence has gone from something that was seen as sort of a backward, older kind of approach to quite precisely one of the most exciting things happening right now, and which was understood as predictive algorithms using statistics and something called machine learning that had been trained using extremely large, high-dimensional data sets. It wasn't about rules and symbolic reasoning. It was about data and its analysis, and particularly data at scale, at Facebook or Google or Amazon scale or the human genome. So this is what has produced the sort of things that we're struggling with today. So here I have, from this morning, I asked ChatGPT to tell me about the coming into self-consciousness of an AI in the style of Dr. Seuss, which was very happy to do. And then I asked one of the Diffusion B programs to produce images of Princeton students listening to a lecture on the history of AI. And it produced something that it had learned very much. How did we get to this world? So this is a world that is explained and is based on deep empirical granularity. What do I mean by that? It's based on the sensory data, the big coming together of experience, and it's granular in that it's about the detailed things of the world, not sort of extreme simple cases, but rather the full complexity, language in all of its different dynamic meters, the irregularities of verbs, not just their regularities, but at huge scale. And one of the fundamental phenomena of our time is that predictive algorithms that are trained on large-scale data, historical current data, have a very powerful ability to reproduce existing forms of inequality and equality. That is, when there are structural inequalities, for example, structural racism, data at this scale tends to reproduce that. And this is a fundamental sort of ethical and political question of the time. So it's often referred to as dumpster fires of the AI of today. So how did we get here? What made it possible? And what are some of the more pressing concerns about it? So I'm going to give you a kind of whirlwind tour of how we got there after reminding you a little bit about what we talked about in our first AI lecture. So now, as I said, AI has been redefined. If you look at the longer history of it, it's a history both of the technical disciplines that are arrayed around this term AI, and it's a sort of a fascinating moment of a cultural focus of thinking through fundamental issues of the nature of humanity, of the nature of culture, of the interaction of nations, of corporations, and sort of things. And its history, those two histories are deeply intertwined. And we need only think of all of these sort of cultural touchstones to think about how much of popular culture is involved in conversations about AI. And as I'll talk at the very end, these very touchstones are important in thinking about real AI today. So let's return to where we began our conversation last time, which was Alan Turing and some of his friends at Bletchley Park doing cryptography during the Second World War. Now, they were knee-deep in doing large-scale computational work on vast amounts of data that was produced by the collection of the signals, the communications of the Axis powers. As one of them described, in doing cryptography, they were, quote, up to our elbows in automation of one kind and another. And in the evenings, they thought about what the implications of this would be in the future. Now, I told you that they broke this into sort of several different ways of thinking about what it might be to be intelligent. One was learning from experience, like collecting lots of signals of Germans making secret transmissions. The other was thinking about rules, logic and mathematics. Many of them came out of domains like mathematics. Now, in the history of the first, say, 50 years of AI, the focus is largely upon rules, plus a small number of facts, not the complexity of experience. And the keynote moment for this is a conference in the middle of the 1950s organized by John McCarthy. And he was quite blunt, and you can find this on YouTube, where he says he invented the term artificial intelligence largely as a way of getting money. Now, as I explained to you, the kind of AI that they focused on was not based on data in particular at all. It was rather focused on a vision, in some sense, the self-image of mathematicians and logicians and chess players. And it prized the ideas that what really made human intelligence interesting was its high symbolic nature. So the forms of computing programming they devised and tried to combine rules, symbolic reasoning, and a certain amount of facticity, and it was made into the heart of intelligence. Now, what happened to the learning from experience? Well, I've already told you McCarthy was down on this, and so down on was it, he and his allies, that they went after the biggest examples of it. So this alternate path is most identified with an apparatus called the perceptron, which was an attempt to literally reproduce in machines a kind of neural network that would sense things and try to say whether what you're seeing is an A or an H. Initially, it was a large machine, but it became something that was very much algorithmic. For McCarthy and his allies, this was the antithesis of what artificial intelligence would be. And I already quoted this for you. It was to get at the lowest level of human and animal cognition, and not its heights, the symbolic heights. So they deliberately targeted for death, quite successfully, and argued that the data-centric approach was not intelligence worth the name. Okay, so that's all for review, and I'm casting it in two black and white colors. So our question today is, how did this data-focused approach come back? Where did it come from? How did it come to dominate in the ways that it does in our world? Well, you'll remember in Bletchley Park they talked about rules, but they also talked about learning from experience. They were in the heart of a data-driven enterprise. So when we think about Alan Turing, typically the stories are about Alan Turing, the lone genius, the tortured genius, the person who suffered this awful persecution by the British state. But his work was very much done in an entire factory that I described to you some weeks ago, of data analysis at large scale using large infrastructures for the purpose of attempting to win the war. This approach to thinking about data did not disappear, but it wasn't known as AI at all. In fact, it was something very different. Now, the AI of our current moment emerges from a long lineage of there and has a bunch of components, only some of which I'm going to be able to talk to you today. So the AI of the past half decade, it very much emerges from a data-centric approach, and it's enabled by relatively weak privacy and intellectual property protections. We've been talking about this. It's coupled to an organization of research labor, and it's undergirded by massive computing capacity. You need all of these ingredients to understand the emergence of AI in our terms. And the roots of that are very much in this World War II context and what happens to it after the Cold War. So while the symbolic rules program is exploding and getting most of the good press, behind the scenes, mostly in classified domains, there's a kind of low road of instrumental computational data, which is vast archives of data, first things like cryptography, cryptological, combined with an approach using statistics, where the goal is not necessarily to produce great scientific thoughts, but rather to solve concrete problems of the military. It develops in lots of different places, and this is just one kind of example, which is a domain that becomes known as pattern recognition. And in pattern recognition, you have fundamental issues like vast amounts of imagery from satellites and spy planes, and it takes vast amounts of human labor to classify them. Would it be possible for a computer to learn to classify this? This was not intelligence in the sense of, can we reproduce the great mathematicians of the past, but rather, can we reproduce the labor of recognition on a computational platform? This approach developed into a whole array of algorithms, and any of you who've ever studied machine learning or computational statistics have learned many of these algorithms under various kinds of names. And it concerned using those kinds of algorithms on large data sets, not kind of toy data sets that were more the focus of mathematical statistics. Now, this issue of how is it that you replace an expert was one that was extremely challenging. And the people in symbolic AI definitely wanted to do this. And the people in computational statistics wanted to do this. And it turned out to be very, very challenging. One of the great discoveries, and it happens in parallel in computer science and in the social in domains like history and sociology, is a recognition that getting people to explain how they are experts and how they make expert decisions, to ask, say, a doctor, how does he or she make a clinical decision, is incredibly hard. There was a kind of hubris that it would be easy to elicit the thought processes of skilled professionals. But it turns out to be enormously hard. And this is a great example of a Stanford study where a guy using a lathe is trying to explain how he uses it. This kind of skilled activity, and it turns out it's enormously hard to do this. There's a program called Expert Systems, which attempt to elicit rules through discussion with experts and put them into place. But it turns out to be both intensively difficult and expensive to elicit the rules, and incredibly brittle. They're not expansive, they're not good at dealing with the complexity of the world. And they call this the knowledge acquisition bottleneck. So you needed a human expert to discuss for a very long time with a so-called knowledge engineer in order to elicit rules. And it came to dawn on a lot of people that the solution might not be to try to replicate the rules by which people think, but rather to create predictive algorithms that might work in an entirely different way that would duplicate at a very high percentage the kinds of decisions they would make. One of the interlocutors of Turing, way back in the 40s, wrote in 1985, "Mastery is not acquired by reading books. It's acquired by trial and error and teacher-supplied examples. This is how humans acquire skill." And if you think about this, this is both a statement about what the nature of human cognition and intelligence is, and a concrete program for thinking about what you'd want to do if you were going to build algorithms that would duplicate human reasoning. And the kind of thing they're thinking about, because this may be all very abstract, is imagine you've done a vast sky survey of all the stars at very high resolution. And traditionally, you'd have astronomers, and as we discussed, traditionally, large pools of extremely learned women look through all these plates and classify stellar objects. So the question was, could you do that? Not by asking the astronomers, how do you tell a pulsar or not, but taking a large data set where they classify objects and then produce a statistical predictor that's going to make the predictions of what the astronomers would do. Now, I hope that's clear. It's not saying, how do you do it? It's saying, can we mathematically model something that's going to make predictions that line up with you? That division is a really major one, because it no longer means that you're attempting to model the process of human cognition. You're attempting to model the outputs of human cognition. This turns out to be more successful than anything that had been produced in the rules-based AI. And for those of you who've worked in the CS world, it consolidates into what we think of as central parts of machine learning, and particularly what is called supervised learning. And supervised learning is one in which you have a set of data that has been classified by a set of human actors, and you produce algorithms that can duplicate that classification. So think sky charts, or if you had a whole bunch of people assessing credit card applications, then you build an algorithm that models that behavior and can do it at an incredible scale. Now, all of this was going on in all kinds of academic and intelligence settings, but things were happening in parallel that we've been discussing in the past few weeks that created the conditions in which these technologies could be applied at a much larger scale and become familiar to all of us. Those shifts involve, first, as we've discussed, the consolidation and expansion of vast infrastructures for the storage and analysis of data. The particular focus on storage of data was one that was businesses and spies were much more interested in than a lot of scientists. But an infrastructure comes to be built and expanded, and it continues to expanding to this day. So you had to have this infrastructure. But you also had to have a change in norms about using data. And I think I showed this to you some weeks ago, but it's a meme making fun of the fact that in the 1960s, there was this thriving concern about the privacy of our data. And yet today, we expect the wiretap on our desk or on our wrist to answer sorts of questions. There was a transformation of norms. And this was very much connected to those transformations in the laws around privacy that we discussed. This particular important moment in 1974, where it seemed that the United States and other jurisdictions would have robust privacy laws, but that's not what ended up happening. The commercial data, by and large, was available for use by commercial entities, for use, for sale, for analysis, and whatnot. And it's central to the world in which we live. So you had this new technology, this new kind of predictive technology, combined with ever greater infrastructures, changing norms around privacy, relatively weak laws around privacy, and with the explosion of the internet, the incorporation of large companies that retained this data, stored this data, and had many reasons to be using it. Oh, and I forgot that the US government itself came also to have very controversial accounts of what kind of data it could and couldn't use about US people and non-US people. So in the technical world, and in the business world, and in the cryptological world, we've moved very, very far from the world of rules that I discussed before. In fact, an ethic that focused on predictability, prediction, over interpretation, over algorithms that could predict on the basis of large-scale databases, came to be seen as not just good in a commercial domain or good in a military or intelligence domain, but the best and most fundamental kinds of algorithms, sort of very legitimate objects, even though they were so far from the visions of what intelligence had been in more traditional AI. One of the touchstones of this transformation came in 2009, so the year of that Google paper. So Netflix had announced a few years before a crowdsourcing challenge. And what Netflix said was, we are going to give $1 million to the team that can best improve our predictive algorithm. And at the time, Netflix wasn't streaming, they were sending out DVDs. And so what happened is a wide variety of people gained access to an extremely large, at the time, data set, a kind of commercial data set. And at the time, it was quite difficult for ordinary, say, programmers or researchers or others to gain access to large-scale commercial data sets. Only the big players, the Googles, the Facebooks, the Amazon, and the Netflix had access to this kind of data. Netflix released this, and then said, see what you can do. And the story is quite interesting. People tried all kinds of algorithms to try to interpret it and then try to predict on the basis of it. And various people came together into teams that would combine their algorithms. Now, the winning approach, the group here that's called Belcour's Pragmatic Chaos, didn't have one predictor. Rather, what they did is that they produced a giant prediction engine which combined 500 predictors, 200 blends, combined with another 30 blends. Now, this algorithmic prediction system was able to better predict the kind of movies that people liked. But it was, from the standpoint of any traditional scientific approach to knowledge, bizarre. Because it was just this almost random seeming combination of all kinds of different machine learning and statistical classifiers that were rammed together and that worked. It it was an object that fundamentally was predictive without giving you much understanding at all. But it was really a touch point in the power of what you could do if you harnessed a large amount of computational power, a large data set, and lots of predictors to make predictions along one particular metric. So it was at once a moment in which this ethos of prediction gained a sort of widespread attention, but it also was a model for how you might organize research itself. Now, the Google paper I began with said that we'd been looking after the wrong kind of knowledge, that language is this sort of granular, complicated thing, and we needed to create knowledge systems that recognize that. The Netflix challenge sort of doubled down on that and said, the way that we do that is not through, say, individual geniuses thinking and figuring out theories, but rather collectivities whose results contribute towards a larger project of coming together and trying to maximize some form of metric. The Netflix challenge then modeled an idea that lots of people would come together and in a competition in trying to maximize something, do better than any one group could do. And in fact, that you could combine this. This meshed perfectly with organizations who had fundamental metrics at the heart of their business. For example, I have a misprint here, but if you think about Facebook, Facebook becomes very early engaged in maximizing engagement on its website. That is, its goal, in some sense as a business, is to have the largest number of people who spend as much time as possible on its website, and thus its algorithms were designed primarily with that in mind. That is a single metric. Now, this is called the secret sauce of machine learning, and it turns out to be enormously, spectacularly powerful, far more so than anyone ever had any right to think was going to be the case. And it works in any domain in which you can select an agreed upon metric and maximize it, whether it's engagement, whether it's a score in predicting what people like, or things like how to get high scores in game, or indeed fundamental scientific issues. So in 2012, that neural network approach, which I showed you had been outright attacked by people in the symbolic tradition, came back with a vengeance. It was rebranded deep learning at first. And it's deep because it was a form of network that had many layers. And I won't go into the technical details, but what those many layers allowed it to do was overcome some of the formidable problems of a much simpler neural network. Last time I told you that it couldn't, neural networks can't figure out, simple neural networks can't figure out how to discriminate, how to replicate what's called an XOR function. But if you have many layers, you can. Now, people had known this in some sense for decades. But what they didn't have were three things. They didn't have enough computer time to train a neural network, because training a neural network is slow, computationally expensive, and expensive in terms of electricity. So they didn't have the compute time. They also didn't have data. Neural networks require huge amounts of data. To train a neural network to recognize a logical function takes a huge amount of data. To train a symbolic machine to a logical thing is no data at all. So they required lots of compute time, it required lots of data, but also neural networks had always been suspicious. Why were they suspicious? Because you cannot, most of the time, figure out how it is that they are making the predictions that they did. Now think back to that Netflix predictor I showed you. That predictor was this congeries of all kinds of predictors. It was no model telling you, giving you an understanding of people's cognitive states. It was a purely predictive kind of thing. Well, so were neural networks. And in fact, neural networks turned out to be even better if you had the sufficient computers and cache to run them, and energy to run them, and data to them, and you didn't mind if all you got was prediction. And by 2012, there were some very, very large corporations that had exactly that combination of elements. And hence, deep learning, or neural networks, explodes onto the scene and turns out to be enormously good at a huge number of tasks. Tasks that we use all the time, from voice recognition to recommending what kind of websites you should see on any of your on any social media, to fundamental questions of thinking about protein folding, to indeed questions of understanding language itself. And above all, there was a moment in which there was a large database of images, and the deep learning algorithms just blew the other algorithms out of the water when trained on a huge amount of visual images. It was thus that deep learning and this entire approach gets rebranded in 2015 as AI. Now, as I said to you, AI, for many people from the 90s through the aughts and into the 2010s, was kind of the old-fashioned, old hat. It's precisely not, which was exciting and important. But AI has always been a branding tool. And the explosion of powerful neural networks on extremely large computational platforms with large amounts of data, with fundamental predictive problems, turned out to be just the recipe for a rebranding of all of that as artificial intelligence. And it happened relatively recently. And that produces what we are dealing with now. So the platforms that we've become so familiar with in the last couple of years, notably ChatGPT and then image production, are descendants of these. And like the other even more so than deep learning networks, they depend on vast amount of computational power, truly tremendous data sets, and they're fundamentally a predictive model. The numbers are so vast, though, that only a small number of companies and an even smaller number of nation states are capable of training these kind of models. They also depend on a really fantastic technical trick that is first published by Google in a paper called "Attention is All You Need," that allows you to connect large data sets and give them a kind of memory. But it's what allows us to ask these kinds of questions. So when you think about ChatGPT, or all of the phenomena like it, just keep in mind it depends fundamentally on truly vast infrastructures of compute, large data sets, and a willingness to pursue a kind of predictive ethic. And the amazing thing is that it turns out to be enormously good at producing natural language. It's actually unbelievably surprising. So the paper I began with, the Google researchers say, it is a really strange state of affairs that the world is set up in such a way that we can learn so much from data. And whatever the effects of ChatGPT and its like in the next 100 years, one of the most reaching aspects of them is it challenges our own vision of what it is to know something and the nature of the world. Language is such, it turns out, that an algorithm which essentially predicts what the next letter should be is capable of producing language that we register as almost human-like, and is capable of organizing things that is almost human-like. Those are the epistemic implications. And how those will play out, it's going to be for all of you to decide in some sense. Now, there is a massive conversation going on about the implications of this, because the deep learning hasn't just been rebranded as AI. It's that we are all exposed to things that are starkly better than anything most of us anticipated might exist in our lifetime. And this brings us back to this bigger conversation and how we think about AI. When we think about AI, we don't think about it neutrally without sort of a broader cultural conversation. And here, I've just given you, these are just films, but of course there's as many books, and including things like The Burning Chrome. Now, the conversation right now, there's a very vibrant conversation about the harms and dangers of AI, potential and current. And just last week, I think it was, 2 weeks ago maybe, there was a major AI summit, nowhere less than Bletchley Park, where a large number of leaders came together to sort of make statements about thinking about the powers and harms of AI. And at the same time, questions of AI dominance very much structure a lot of facets of trade policy, particularly of the United States vis-a-vis the People's Republic of China. This conversation is a bigger one than I can deal with in this lecture, but just to conclude, I want you to think about two major schools that are really important and central in the conversation. And if you're going to get into this conversation, you really need to wrestle with both of them. The first emerges from groups of people who've been concerned with how automatic decision-making systems are going to affect people in the here and now. You remember back in my lecture on privacy, I talked about how people worried about privacy and data, both against the state and against corporations, noted that data was most often going to be mobilized against the least empowered sets of people. With the explosion of a data-based economy, data-based governance, this has turned out to be very, very true. Whether it's in systems for judging whether people are going to be recidivists, or in building facial recognition systems, the everyday systems all around us, most of which we don't even think of as AI, but now are classified as AI. One of the famous science fiction things is a movie based on a Philip K. Dick story called Minority Report, in which, in the movie, Tom Cruise plays someone who uses what are called precogs, who judge and predict where crime is going to appear and stop it before it happens. This mode of thinking is very powerful in thinking about the attempts to create predictive algorithms that say crime is likely to appear here, when those predictive algorithms are based on historical data that is very much grounded in the very inequality that are all around us and that frame our entire society. So you have a whole packets of civil society, people in governance working at this level. And it's among the most important conversations happening right now. In the last couple of years, another way of thinking has really come to the fore, and it is very much grounded in the narratives of existential risk that run through so much of science fiction, particularly popular science fiction, as in The Terminator, where Arnold Schwarzenegger's character comes back in time to kill the person who is going to defeat the machines. So there's a big conversation that has been fed by a lot of large tech money that is worried about AI algorithms as a fundamental risk to the species itself. And these two camps do not see much eye to eye. One is very much concerned with questions of, say, drones and policing in the here and now. The other is worried that we won't, say, make it to Mars if the machines kill us off. These are both central conversations, and they really illustrate the way in which the cultural conversation around AI is going to be enormously important in the subsequent development of its technology. Okay, so for next time, we are going to be talking about how this cluster of predictive algorithms came to shape the web. So in the last couple of lectures, we've talked about the transformation from the true vision of a peer-to-peer, true democratic internet And we're looking at how is it that it became the very different internet in which we live today. Central to that story is the predictive algorithms that recommend the content we see, that create the informational ecosystems in which we live, the differential, if economic and informational infrastructures in which we live. But that story is equally one about how shaping the web in order to gain money was central in creating the very infrastructures that made these predictive algorithms possible. You don't have a chat GPT, you don't have Google search, you don't have Facebook prediction algorithms unless you have the capacity to create infrastructure that is based on huge training data, grounded in relatively weak privacy and intellectual property laws. And we need to track this in order to understand it. That is what comes together to produce AI. Okay, I actually do have time for questions today, so anything. Yeah, please. Yeah, oh, so the positive effects, right. Well, so the question is, what about the positive effects? Yeah, I haven't played those up, but there's no question that, you can think about them in a variety of places, but there's very easy ones, like the fact that voice recognition now works so enormously well. And that is a fundamentally accessibility producing technology, right? It is utterly transformative. We will probably get over a kind of a shock and awe about GPT and other sorts of things and see those as fundamental tools, just like calculators are tools. And then, of course, in a wide variety of sciences, there's incredibly rich databases that previously were not tractable. So we simply can do very different kinds of science, whether it's protein folding or other kinds of things. So you're absolutely right that I haven't played that up as much. Now, some of that's pretty contested because, as I told you, the explosion of machine learning, now AI, is focused on prediction. And for many scientists, prediction is but one part of the equation. When you're fundamentally interested, say you're interested in chemical mechanisms, that you're able to make predictions about those is not the same as providing a chemical mechanism. So in discipline after discipline, you see often a tussle between new kinds of science, which are predictively powerful based on huge data, and forms of reasoning which are based more on, say, causal modeling. And the funny thing is, this happens not just in the sciences, but it very much happens in commerce. So one of the earliest great successes in much of this, when it wasn't even machine learning, it was just called data mining, was replacing traditional experts at marketing at, say, a grocery store or a drugstore with the predictions of an algorithm says, actually, it makes sense. This is the most famous anecdote. It would seem counterintuitive, but if you put diapers and beer together in a late-night drugstore, you're going to sell a lot more of both. And a way to think about that is you're changing the kinds of expertise about fundamental decisions, and it crosses the sciences, the humanities, and all kinds of business practices. And we're going to see continuing tussling over the strengths and weaknesses of those different kinds of approach. So that's a wonderful question. Other thoughts? Yeah. Ron.
So this is asking you to do a little bit of future casting, I guess. Yeah. But you were mentioning these biases from our society that are making their way into these large data sets. And Dr. Ruha Benjamin here at Princeton coined the term garbage in and garbage out. And I wanted to know your thoughts on, how would we eventually overcome that in terms of large data models moving forward?
So the question is, if you have lots of garbage in your data set, how are you going to prevent lots of garbage coming out? And this is an active problem, and it's easy to portray it as a kind of divide between those people who recognize these things and those who don't. And how are those being resolved? Well, it's a major research issue. And there are some people who think the answers are going to be technical ones. And so there's an entire enterprise within computer science that is committed to making algorithms more fair. And some of the great work is being done here. Now, it turns out, and it's more technical than I could get in this class, the technical definitions of fairness are logically contradictory. So it always has to come down to a human policy decision. But it's very clear that the solutions to this are not going to be merely technical. They're also going to be in the right kind of collectivities. We don't know a lot about how ChatGPT works under its internals. Part of it is a engine, as I explained, that works on these kind of it's called semi-supervised learning, and so it's learning a lot of awful aspects that are hardwired into the large language corpus. But if you try to get ChatGPT to do a lot of things, it will utterly refuse to. And you, for example, because I'm a deep geek, I asked it when it first became, I wanted it to make lots of evil constitutions of the United Federation of Planets, because of course I did. And it wouldn't do it for certain keywords. So clearly there had been a work to hardwire it to prevent certain inegalitarian outcomes. But when I asked it to use, sort of Plato has this tripart division of society, which is a non-egalitarian society, it didn't hit any of those keywords and it happily produced an egalitarian. So some of the solutions may come from sort of hardwired sorts of things. Some of them may come from really transforming the kind of data sets and recognizing the inequities in data sets, but that's incredibly hard. So for example, it's trivially easy to show that if you have a large data set and you remove race from it, completely in the United States. Zip code is such a powerful proxy for race, you're still predicting on race. So it's a very hard technical and non-technical problem. It is one of the great challenges of our time, especially if your attitude isn't one that we're just going to get rid of all these algorithms. If we say these are going to be built into our decision systems, then it's incumbent on all of us, technologists and the like, to produce outcomes that comport with the kinds of societies we want. Great question. Let's see. Yeah, we probably have time for one more. Please, John.
How do you see the push for automated general intelligence fitting into the conversation of symbolic reasoning versus predictive AI that you spoke about?
Well, so people are still really fighting about this. So a lot of the people in more traditional AI and then people in cognitive science are quite explicit that whatever ChatGPT and all the foundation models and all of the image models and the variety of other technologies, which I'm just capturing under those terms, they still can't do basic things like logical reasoning, complex arithmetic, a whole array of things that we think are essential to human intelligence. So whatever they are, they're enormously good predictive. Well, one term that someone uses is, that a group of researchers uses, they are stochastic parrots. And they're never going to be more than that. As a historian, what you see is a continuation of this long-term division between accounts of what it is to be intelligent. And what is so shocking in some sense about these generative models is how many domains they approach, they perform better than anything the symbolic people thought could ever be produced. But at a fundamental level, they do not, to many people, they just will never be intelligent the way we understand intelligence to be. There's a whole other way of looking about it, is that in the past 30 years, we've come to know so much more about the diverse forms of intelligence in the animal world that it's my prediction is that we will come to appreciate and taxonomize different forms of animal intelligence, different forms of machine intelligence, and different forms of human intelligence. Rather than seeing them as an either-or, we're going to recognize this explosion of different kinds. And the one that I'm talking about today is this rather remarkable, vast empirical collection that can generalize and produce on the basis of incredibly large data sets. Okay, our time is up. I actually finished on time. Next time, as I said, we're going to look at what happens when these sorts of things are built into the web, and indeed, the companies that produce them, the platforms, are precisely the ones with the money, compute, and data to produce these kinds of things. It's very much part of our situation. So I will see you all on Thursday. Thank you.
Thanks for listening to this week's Lectures in History podcast. To find even more history content, visit c-span.org/AHTV.